Okay, so today we're going to be talking about the scatter plots, correlation, and analysis of these scatter plots, and you'll need this for your project. Remember last time I showed you the trifold, and they had the scatter plots that were relating, for example, price to square feet in the house. I'll set that out a little bit later too for those of you who missed last class, but we did start collecting data last class as well. Okay, so I don't think we have a ton of Project 3 presentations today, but we have at least one. We'll see. And we're going to talk about correlation coefficients and analyzing scatter plots. All right, so has anybody visited Yellowstone National Park? Raise your hand if you've visited Yellowstone. One person? Okay. So they are famous for their geysers and their thermal water features. And this is probably the most famous geyser in the US, Old Faithful, named that because it faithfully erupts on regular patterns. And the patterns are actually bimodal, meaning that it's either going to be about 60 minutes or it's going to be about 90 minutes in between the eruptions of the geyser. And so they can actually predict if it's going to be 60 minutes or 90 minutes based on how long it takes to erupt each time. So a longer eruption means it's going to wait longer until the next one. And we'll see that on the next slide, but we're going to watch this short video about Old Faithful. I'll fix your volume for you. Maybe. I might have to pause it to do that.
People normally go on vacation. They have a schedule that they use. So we're going to have lunch at noon or 1 o'clock. We're going to go scuba diving at 3 o'clock. And we're able to use the clock to base our activities on. But here at Old Faithful, we don't use the regular 12-hour clock that everyone else uses. It's all about Old Faithful. So when people choose to have their lunch or their dinner or their nap or their walk through the geyser basin, all is based on when the Old Faithful is going to erupt, so they can be sure and see it. Old Faithful is getting ready to erupt, so I am trying to time it. Oh, and there it goes. So I'm hitting the stopwatch, and I'm noting the time on the atomic clock at 12:58, which is pretty good considering that the prediction was 12:59. So we're getting closer and closer. Now I'm going to measure Old Faithful. So as the plume of water gets higher and higher in the window, I'm comparing it to this tree right over here. And I'm using this picture, which has a triangulation set up, to identify how high the water went on the tree. And what I figured out, Old Faithful's hit its peak already, was that it came to about right here, which is about 140 feet. So in the logbook, in addition to the start time, I'm going to record 140 as the height of this Old Faithful, which is the tallest one today, which is kind of nice. And then all I need to do is keep an eye on the timer and see how long Old Faithful lasts. And that's all going to determine how we predict the next one. I'm also going to record the interval between the last Old Faithful and this one, which is 89 minutes. We take those intervals and we use those to make our average. Basically, we use observational Old Faithful to figure out how to predict it. And it changes through time. Just a couple weeks ago, we were using 88 minutes for a long eruption. And now we're using 90 minutes because we figured out that that was going to give us the better average. So Old Faithful is now been going for 1 minute 48 seconds. It's still going strong. If it lasts longer than 3.5 minutes, then we have what we call a long eruption, which is the most frequent form of Old Faithful eruptions. It's a bimodal geyser. It has longs and it has shorts. If it's going to have a short, I would expect that any minute now it would just suddenly stop. If it were to do that, I would go ahead and predict it for 62 minutes. But it looks to me like it's probably going to be a long. Still a lot of water coming out of it. We're at 2.5 minutes now. So We're gonna wait another minute and make sure that Old Faithful is a true long. We're getting to the point where the water's pretty low right now, so I'm gonna be using the binoculars to determine the difference between the water and the steam. We won't consider the eruption done until there's no more water coming out. So we're still getting kind of big spurts of water coming out of Old Faithful. Most of the people have turned away now, and we are at 3.5 minutes. So we're going to consider this to be a long eruption, but I am going to wait and record. Okay, and it's done. So 3 minutes, 42 seconds. So our start time was 12:58. So our next prediction would be go 1:58 and then go to 2:28. All right, 2:28 in the book. And then the next thing I have to do is tell the world. This is 724 Victor with the Old Faithful prediction. Old Faithful geyser is predicted to erupt at 2:28 p.m. plus or minus 10 minutes.
Okay. So let's get back to the math of that. Let's look at the scatter plot here. So we have duration and interval. So you can see that the ones that last longer mean that it's going to be a longer interval before the next eruption of the geyser. So one way to analyze this graph is just to describe that trend. As the duration increases, the interval does what? It also increases, right? The other choice would be that it decreases, but in this case it is going to increase. So we're going to put that there. As duration increases, interval increases. And then you should also know vocabulary for variables in statistics. The variable, the independent variable on the x-axis is called the explanatory variable. So in this case, what's the explanatory variable? Duration, very good. The response variable is the dependent variable. It's on the y-axis, and this time it's called interval. Good. Okay. Questions? Okay, so think about this one. As the number of missed classes increase, the exam score does what? Decreases. Good. So these are not that tricky. And they will be part of the analysis of the graphs that you put on your trifold. But there'll be more. Okay? How about this one? As variable x increases, the numbers for variable y do what? They increase. Very good. All right, and how about this one? What's the correlation between the number of seashells and the number of friends you have? Very good. There is no correlation between the number of seashells you have and the number of friends you have. Unfortunately, seashells do not buy friends. No. That was my whole plan. Okay. All right, so we can also describe the correlation with the Pearson coefficient. And these are actually exact numbers. So we're not going to, in general, we're not going to guess at a Pearson correlation coefficient, but it is good practice to make sure you understand them. When we do your charts on your trifold, we will have Desmos calculate your correlation coefficient for you. But here are some examples of what they might look like. So the R values show you both the strength of the relationship and also whether it's a positive or a negative relationship. So you can see that this one is very close to a straight line and it's going with a negative slope. and the R value is negative 0.99. So R values are going to be between positive 1 and negative 1. Positive 1 shows a very strong positive relationship. Negative 1 shows a very strong negative relationship. And what does a 0 show? No correlation. Very good. All right. So negative 1 is strong. Positive 1 is strong. Close to 0. Not a relationship at all. So I see that a number of you are on the slides, and what I want you to do is try to see if you can guess the correlation using this as a reference point. All right, if you're not on the slides, let's join the slides now. And I'm wondering if we get like unique ones or if everybody's looks about the same. Does yours look like this or does yours look different? Different, cool. All right, so give it a try. And if you don't get 100%, feel free to try it again, get 100% the second time. Okay, so let's read this problem together, and then I'm going to have you talk with a partner and see which answer you think might be correct. A national consumer magazine reported on the following correlations. The correlation between a car's weight and its reliability is negative 0.3. The correlation between a car's weight and its annual maintenance cost is 0.2. Which of the following statements are true? 1, heavier cars tend to be less reliable. 2, heavier cars tend to cost more to maintain. 3, car weight is related more strongly to reliability than to maintenance cost. And then you can see your choices. It might just be one of them, or it might be 1 and 2, or it might be 1, 2, and 3. So take a moment to think about that. Okay, raise your hand if you chose A. Raise your hand if you chose B. Raise your hand if you chose C. Raise your hand if you chose D. And raise your hand if you chose E. All right, so we had more votes for D and E. We also had some votes for B. So let's go through them one at a time. Heavier cars tend to be less reliable. That would mean that there's a negative relationship between the heaviness of the car and the reliability. Is that true?
Yes.
Yeah, there is a negative relationship. Good. All right. 2, heavier cars tend to cost more to maintain. So there should be a positive correlation between the heaviness and the cost. Is that true? Yes. Now, if we go back, we'll see that they're both pretty weak correlations, right? They both land in the weak range, but they're still correlations. Let's see. Car weight is related more strongly to reliability than to maintenance cost. So which one has a stronger reliability here? I'm sorry, a stronger correlation? The reliability one, because this is closer to negative 1 than this is close to positive 1. Or you could say this is farther from 0. So this is the stronger relationship, and that's what it says, right?
Yep.
All right, so everybody got part of this right. All right, everybody chose one part that was correct, but it turns out that they were all true statements, so we should have chosen E. Let me draw a little scribble around that. Okay. All right. So let's look at this one. I can't remember if we're going to do what type of correlation it is, but we might as well try. So is it going to have a positive or a negative R value? A negative 1. And what kind of correlation do you think it might be? Do you think it's going to be in the very strong, moderate, weak, or very weak? Yeah, I heard strong and very strong. And I can't even remember what I wrote under here, but we're about to find out. So this scatter plot shows a strong negative linear correlation or linear association between the age of the drivers and the number of accidents. They don't appear to be any outliers. Outliers can actually really affect your R value, and that's a good thing to remember. because most of the data might be pretty well correlated, but then you get an outlier out here and it's going to really mess up your R value. In this case, though, we don't have any outliers. All right, so make your choice in your head. There is a strong positive linear association between the two variables. Is it A?
No.
Is it B?
No.
Which is it?
C.
Yeah, it's C. Very good. This one is a negative association. This one is not strong enough, so C would be the best answer here. There is a moderately strong negative linear association between the two variables with a few potential outliers. So moderately strong, and then look for the outliers, and I'll have you vote in just a minute. All right. You're looking for moderately strong, negative, and outliers. Raise your hand if you chose A. Raise your hand if you chose B. Raise your hand if you chose C. All right, of those of you who voted, you all got it right. That's good. You can see the outlier over here and over here, and then the rest of this is that moderately strong data. Excellent. One more. All right, so everything that we're going to do for your projects is going to be linear relationships, but this one's talking about a nonlinear association. So I want you to remember that not every association is linear. So this says there is a strong negative nonlinear association between the two variables. Strong negative nonlinear. All right, raise your hand if you chose A. Okay, raise your hand if you chose B, and raise your hand if you chose C. Okay, all right. So strong means that they should be kind of making a shape. This one's a little bit too spread out to be a strong relationship. Negative does mean that as X increases, the Y should be decreasing. And nonlinear means it shouldn't be just a straight line. So nonlinear means it might have a curve to it. And this is the right one. Good. All right. So we're going to be using those in our project analysis, but we still are working on collecting the data. So that's what we're going to do next. And then we will go back and do some presentations if we find out that there are some that are ready for today. Okay? You are only responsible for your own, so if your partners are absent, they'll get theirs next week. Any questions? If you were not here last class, find the spreadsheet that your partner shared with you and just ask for some advice on what you should be doing.